Hello, welcome to my video series of algorithms. This is part 3 of Module 4, Greedy Algorithms. In this video, we will continue our discussion on the shortest path problem and Dijkstra's algorithm. We will prove the correctness of Dijkstra's algorithm. We will also present its implementation details and analyze its time and space complexity. Let's quickly review the shortest path problem and Dijkstra's algorithm. Given a weighted graph with no negative edge and a single source node, the goal is to find the shortest path from the source node to all other nodes. For example, we can represent the US map as a graph, where the nodes are the cities and the edge weights are the toll fees to travel between cities. The source is our current location, and we want to find the cheapest route to travel to different cities. Dijkstra's algorithm solves the shortest path problem using a greedy approach. It progressively visits a new node that has the minimum total cost, which is calculated using the formula highlighted here. The total cost is the sum of the existing cost to reach the visiting node U, or DU, and the edge weight between the visiting node U and the new node V, or LUV. Recall the example we discussed in the previous video. Here, all visiting nodes are marked red, and all candidate nodes that can be reached are marked green. The total costs for visiting the candidate green nodes are shown in the top left table. Because visiting Chicago and Kansas City have the same lowest cost, we will arbitrarily select one to visit. Suppose we visit Kansas City. We record that the minimum cost to reach Kansas City is $15. Let's generalize the above procedure. Again in the figure, the visiting nodes are red and the candidate nodes to visit are green. The black dotted lines indicate the shortest path from the source node S to the corresponding nodes. The yellow boundary separates the visiting node set S and the unvisited node set U. We evaluate the total cost of path induced by the boundary spanning edges, marked in red. For example, the total cost of the path induced by the edge U1V1 is the cost of the path SU1 or DU1 plus the weight of the edge U1V1 or LU1V1. Then, the algorithm will visit the candidate node with the minimum total cost. For example, if DU2 plus LU2V1 is the minimum total cost, the algorithm will visit V1 and record DU2 plus LU2V1 as the shortest path length to V1. The main concern about the correctness of Dijkstra's algorithm is ensuring that there exists no shorter path via unvisited nodes. For example, how can the algorithm assert that the path indicated by the gray broken arrow is longer than the path SU2V1, given that we have not seen it yet? So, the correctness proof needs to show that the path SU2V1 is shorter than any of the alternative paths. Consider the alternative path indicated by the gray broken arrow, which starts from the source S and ends at V1. Since S is in the visiting node set S and V1 is in the unvisited node set U, the path must contain a boundary spanning edge. Let such an edge be xy. In this case, the path length from S to Y is dx plus lxy, where dx is the shortest path length from S to X, and lxy is the edge length between X and Y. Note that the form of the equation for calculating the path length to Y is similar to the equation used to calculate the total cost to V1. Because xy is also a boundary spanning edge, the path induced by it should have already been evaluated together with path induced by other boundary spanning edges, like U1 V1 and U2 V1, etc. According to Dijkstra's algorithm, the shortest path among all paths induced by boundary spanning edges is selected. Therefore, if the algorithm has picked the path S U2 V1, it means that this path is the shortest. In other words, we have du1 plus lu2 v1 less than or equal to dx plus lxy. Also, recall that there exist no negative edges in the graph. Therefore, the purple path that goes from y to v1 must have a non-negative weight. Denote the path length as PL y through v1. Then we have PL y through v1 larger than or equal to 0. Adding it to the right-hand side of the former inequation, we get du1 plus lu2 v1 less than or equal to dx plus lxy plus pl y through v1. Consider the inequation. The left-hand side is the total cost for visiting v1 through the path s u2 v1, or the pink path, which is provided by Dijkstra's algorithm. The right-hand side is the total cost for any other path, or the yellow path. Hence, the inequation tells us that to reach v1, the pink path is always shorter than or the same as the yellow path. In other words, the path provided by Dijkstra's algorithm is always shorter than or the same as any other path. It follows that the path provided by Dijkstra's algorithm is the shortest path, and the algorithm is correct. Next, let's discuss the implementation details. Recall the scenario shown in the figure, where the red nodes are the visiting nodes, and the green nodes are the candidate nodes to visit. We pick the minimum path and visit Kansas City, and then record the total cost as its shortest path length. After visiting Kansas City, we may be able to visit new cities or reduce the total cost of visiting some existing candidates. For example, through Kansas City, we can visit New York, and we can reduce the cost of visiting Philadelphia and Orlando. We need to update the top left table accordingly, select the minimum cost, and proceed to the next pass of the algorithm. To summarize what we have observed, we need a data structure like the top left table to store the total cost for visiting the candidate nodes. We need to pick the minimum from the data structure, and we also need to make updates to some of its members. Because both operations are performed in each pass, we would like to make them as efficient as possible. The solution is to use the heap data structure, which is also called priority queue. You can find more information about it online. Here, we only briefly summarize how it works. It is a complete binary tree that ensures the parent is less than both of its children. For example, the root 4 is smaller than its children 5 and 6, and the left child 5 is also smaller than its children 18 and 16, and so on. We call it the heap property. Also, because a heap is a complete binary tree, its height is O log n if it contains n elements. In our case, we use the heap to store the total cost for candidate nodes. The worst case scenario is that we may put all nodes into the heap. In this case, the heap will contain v elements, and its height will be O log v. Given the above property, we know the minimum element must be located in the root. Therefore, the select min operation can be done in O1 time. To update an element, we need to find its proper location in the heap to retain the heap property. We reposition the updated element through an operation called percolation, which iteratively compare the updated element with its parent or smaller child. For example, if we change the last element from 16 to 2, we know its value is reduced, so it will likely go up in the heap. So we compare it with its parent 5 and swap them after knowing that the new element 2 is smaller than 5. Similarly, we will move the element down the heap by comparing it with its smaller child if its value is increased. We can remove the smallest element in this way. To remove the root after visiting the corresponding node, we replace it with the rightmost leaf and percolate the new root down the heap if necessary. Note that the number of comparisons and swaps we make in the percolation operation is at most the height of the heap, which is O log V. Now, we can summarize the main steps of the algorithm. We split the algorithm into passes, where we visit one node in each pass. Within each pass, we take the node that has just been visited. For each of its unvisited neighbor candidates, we compute the total cost using the formula du plus LUV. If the new cost is lower, we will update the information in the heap. After evaluating all neighbors, we can find the minimum total cost in the heap and visit the corresponding candidate node. We mark the time complexity for each step here. First, because each pass of the algorithm visits one node, and we have V nodes to visit in total, the algorithm will run V passes in total. Then, taking the node that is just visited needs O1 time. On average, we say that the node has D neighbors, where D is the average degree of the graph. For each of its neighbors, we can compute its total cost in constant time. But if we need to update the heap with the new total cost, we will use the percolation operation that takes O log V time. At last, we spend constant time to find the minimum value and O log V time to evict it from the heap. Summing up, the fastest growing term of the time complexity is OE log V. Note that here we assume D, the average degree, times V, the number of nodes, has the same order of E, the number of edges. Also note that the time complexity OE log V does not consider the case where D is 0, or the graph contains no edges. To consider this case, we add OV back to it and claim that the time complexity of Dijkstra's algorithm is OV plus E log V. For the space complexity, we need three main data structures. First, we need to store the input graph. We can do it using OV plus E space with an adjacency list. Second, we need a heap to store the total cost, which takes up another OV space. Third, we need an array to record, for each node, whether it has been visited, what is its shortest path length, and which one is its former node in the shortest path. The array again requires OV space. Taken together, the space complexity is OV plus E. In summary, we have proven the correctness of Dijkstra's algorithm. We also presented its implementation details and analyzed its time and space complexity. Thank you for watching, and see you next time.